So let's start the class. Yeah, so today we will first look at a lot of permutations problem. They all look very similar, but then we need to be careful because a slightly different variation in the wording will mean it is a different problem, and then we will need to solve it in another method. So let's do these two problems first. They are related. So the first one is, so there are n people, and then we want to arrange them in a line, and then we want to ask how many ways are there to arrange them in a line from left to right. So this will be what? This will be very simple. So there are n people, right? We want to shuffle them and then make them on the line, right? So there will be n factorial. Okay, we can think of the. So this is just, if you are familiar with permutation, this is just n factorial. This is n people. You want to select n people, and then you want to make arrangement. Or you can think of it as there are n ways to choose the first person, and then there are n minus 1 ways to choose the second one, and so on and so forth. Then this is a simple rule of product, and then we get n factorial. Now the next one is slightly different, okay, but they are related. So this time we want to arrange the people to stand in a circle, in a ring. Now we will. So this is the restriction. So if a certain arrangement can use cyclic rotation to get to another arrangement like this. So this is A, B, C. If you look at it in a clockwise direction, A, B, C. This is also A, B, C, right? Then we will count these two as the same. So they represent the same way. So for this problem, suppose that we still have n people and we want to assign them to stand in a ring. How many different ways to do so? So that, how many different ways such that the cyclic shift will be different. So let's see. If there is just one person, then this is what, right? Nothing to do. Two persons, then this is still one way, right? No matter what you do, it must be A, B. Three persons. Do we have something different? So we can have A, B, C, and we can also have A, C, B, right? And all the other cases, they are the same. They are either one of these two cases. So for three, then there are three people, there are two ways. Four will be a little bit more tedious. So let's do that before, and then we may be able to guess a solution. Okay. So 4 person, what can it be? So we may be having A, B, C, D, and then we may have maybe I don't like B. Oh, maybe I like B, A, B, B, C. Is that okay? Maybe I. So A, the right hand side is B. These are the two ways that the right hand side, so not the right, the left hand side of it, let's say you are sitting around the table. The left hand side of A is B. These are the two only cases, right? So we have listed them. So we can start with AC. So we can have A, C, B, D. And then we can also have A, C, D, B here. And these two are all the cases that A is sitting, having C on the left hand side around the circle. So there are no more. And then we will have A, D, B, C. And then finally we will have A, D, C, D. Right? Yeah, these are the 6 cases that we have. So 6 is what? 3 factorial, right? Okay. So 1 person, you get 1. 2 person, so this is n. These are the number of ways. 2 person, you get 1. 3 person, you get 2. 4 person, you get 6, right? 5 person, you should get, what do you think? It's 24. in general, n, we should get n minus 1 factorial. Okay, now I tell you that this is correct. But then we need to find an explanation why this is true. Okay, so this is good. Once we have a solution, now we start from the solution. You guess, maybe this is correct, maybe this is wrong. But let's say we guess that this is correct. We try to find a way to reason, to understand why this is correct. So n, it's not n factorial. N factorial means that you can arrange everything freely. N minus 1 factorial means that one of them should be fixed, and then the other you can arrange them freely, right? So you can interpret things like this. And this is my way of interpretation. So how do we do the arrangement of the seat? So because A, let's say pick a particular person, let's say A has to be seated somewhere. So let's look at A first. Okay, so let's say this is an empty table. Let's look at A first. Now after A has chosen the seat, then there are going to be n minus 1 choice to select a person on the left of A. And after that, there are n minus 2 choice to select the next person to sit here. Is that okay? And then there are n minus 3 choice, n minus 4 choice, and so on and so forth. So by using rule of product, then we get n minus 1 factorial. Is that okay? Does that make sense? Does that make sense? It's like whenever you see a certain arrangement, we forget what happens. We just look at A. We look at A and see and count the people in a certain direction, like clockwise. And then we will see that there are going to be n minus 1 factorial. Is that okay? Now there is another way. Okay, so this is one way. This is the rule of product. And then let's use another way. This time we can call this a rule of what? Quotient. Okay. So product means you multiply. Quotient means you want to divide. So n minus 1 factorial turns out to be equal to n factorial divided by n, right? Okay, so let's think of another way of solving this. So this time, to make the discussion easier, so let's say there are fixed n positions. So if the people are going to be seated, they must choose a seat here. So let's say there are 6 people, they must choose a seat here. Not like 20 degrees to the right or 30 degrees to the left. It must be like this, okay? Now, we allow these people to sit freely, okay? And forget about cyclic rotation, forget, okay? So how many different ways that people can take a seat in these 6 positions? There will be 6 factorial cases, right? 6 factorial. Altogether 6 factorial. And then for each particular case, there will be 6 cyclic shifts. That should be counted as 1. Is that okay? Okay, so out of this 6 factorial thing, we can classify them into groups. So this is the first group. Let's call it group 1. This is group 2. This is group 3. And so on and so forth. Such that in each group there are 6 things inside. Each of them represents the same, a particular permutation, which is the same under the cyclic shift. There are 6 people here, 6 arrangement here, 6 arrangement here, 6 arrangement here, 6 arrangement here. And our target is to find out how many different groups are there. Is that okay? So the number of groups turns out to be, because each of them has the same number of items here, number of arrangements here, then we get the number of groups will be 6 factorial divided by 6. So this can be a different way to interpret the result. Okay. But yeah, for me, I like this one most. Okay, because division sometimes it will cause some. You need very careful checking. You need to know that something appearing here does not appear in this place. Okay, so in math we call this a partition. So they are every two groups, they don't have any common item, and then all of the groups will include all of the items. So this is called a partition. So you divide things into different parts, okay, a partition. So this is sometimes we need to spend more time to check whether it is really no common elements and so on and so forth. But for this one, this is cleaner. So the argument is cleaner. You fix A, you just fix A, and then everything is like the arrangement in the line problem. So you use the same idea and then you get the result. Okay? So this is it. Good. Now the next question. Okay, so let's see. Let's say this time, and let's say we have three symbols of the sun, and then two symbols of the moon, and then let's say we have four symbols of stars. So these are the items that we have. So altogether there are 9 things. And then we want to arrange them into a line. We want to arrange them into a line. All the suns look the same, all the moons look the same, all the stars look the same. And then we want to count how many arrangements are there. Okay, so how many are there? It turns out this is equal to this one. It is equal to 9 factorial divided by 3 factorial, 2 factorial, 4 factorial. Is that okay? So if you can write down this solution before I tell you, could you? Okay, assuming that you have enough time. So I didn't give you enough time to work on this, but let's say if you are given enough time, if you can write down this, could you please raise your hand? I want to check. Okay, excellent. Now the next question is, how do you explain? How do you explain why? Why is it 9 factorial divided by 3 factorial, 2 factorial, 4 factorial? Why is it like this? Yeah, because you have come across the same problem before, right? Okay, good. This is good. Okay, at least you can remember. Now for this one, I think this is I think there are also 2 ways to explain this. Perhaps more. Okay, but these are the 2 things that I like most. The first one is to look at this problem in a selection way. So to place 9 objects here, we can think of it as, let us first find out which positions should we place the sun. So there are 9 choose 3 ways to place the sun inside this 9 position. Am I correct? Now, no matter which case, after that there will be 6 empty positions, and then we want to find out of these 6 empty positions, which 2 positions shall we choose the moon. And after that, there will be 4 positions left, and we want to find out which 4 positions we should place the stars. But of course, there is just only one way. So to get the number of ways to do this, we can use the rule of products again. We make the arrangement problem into steps. First, choose the position for suns, and then choose the position for moons, and then choose the positions for stars. Okay. So in this case, it will be something like 9 choose 3 multiplied by 6 choose 2 multiplied by 4 choose 4. Is that okay? Okay. And then let's expand this, because we now have the equation of n choose r. So let's see. So what is 9 choose 3? 9 choose 3 is 9 factorial divided by 3 factorial, then there's another term 6 factorial here. Is that okay? And then 6 choose 2 will be 6 factorial divided by what? 2 factorial, 4 factorial. Is that okay? And then finally, what is 4 choose 4? 4 choose 4 is 1. But if you want to write it down, it is 4 factorial divided by 4 factorial is 0 factorial. And then 0 factorial, we will assume that it is equal to 1. Okay, so this is a standard. Okay, so 0 factorial is special. Okay, 1 factorial is 1, but 0 factorial, we assume that it is 1. Okay, for consistency. And then if you look at this, then this 9, this 6 and 6 can cancel, this 4 and 4 can cancel. So what you left is 9 factorial divided by 3 factorial divided by 2 factorial and then 4 factorial. Is that okay? Good. Now this is one way. Another way is, let's assume that all the suns are different. So let's say this is called sun 1, this is called sun 2, this is called sun 3. Is that okay? So they are the suns, but they are different. Okay. We have moon 1 and moon 2. Is that okay? We have star 1, star 2, star 3, and star 4. So all of these stars, all of these suns, they are different. Okay. Now, if I have all these different objects, and then we want to make an arrangement, taking all of them together, how many ways are there? There will be 9 factorial ways. Is that okay? Because they are all different, 9 factorial. Okay, now, but suddenly, let's say, suddenly, the moons are gone. The 2 moons are the same. Now, then what will be the change? So, what will be the change? So, if you look at it, let's say we have sun 1, sun 2, sun 3. Let's say there is a star 4, moon 1, star 2, star 3, moon 2, and star 1. Let's say we have this one and this one. Star 1, sun 2, sun 3, star 4, moon 2, star 2, star 3, moon 1, star 1. Okay. Now, originally, if all of the stars, all of the moons, all of the suns, they are different, then we count this one and this one as different arrangement. Right? But suddenly, the moons are gone. All the moons become the same. So we don't have a 1 here, we don't have a 2 here. We don't have a 1 here, we don't have a 2 here. Is that okay? So suddenly, these two should be counted as the same. Okay, these should be counted as the same group. Okay. So which two? So we put these two as a group because at the beginning they are different, but after the removal of this little thing, 1 and 2 here on the moon, they are counted as the same. Is that okay? And then if you look at it, this is a group. This is a big group. No, not a big group. This is a group of 2 arrangements. Okay, these 2 arrangements will be counted the same. We can also list another group. So as long as you write down anything, you have moon 1 and then moon 2, you switch the moon 1 and moon 2, you get these two arrangements should be placed in the same group. Is that okay? Is that okay? So when the moons are gone, then we should merge things together. We should be counting groups instead of distinct arrangement. Each group has 2 arrangements. So there are going to be 9 factorial divided by 2. Is that okay? Is that okay? We need to divide it by 2. And this time suddenly, let's say suddenly, so there are 2, right? Suddenly when suns are gone, these suns are gone. 1, 2, 3, they are gone. Then suddenly, so suddenly, if this is 1, 2, 3, or if this is 2, 1, 3, or if it is 3, 1, 2, or whatever, any arrangement of this sun, although they are looking different at the beginning, they should be counted as the same now, when the indices are removed. Do you understand my point? So if sun 1, sun 2, sun 3, blah, 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 and then we have another arrangement, sun 2, sun 1, sun 3, blah, 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 the last part is the same, then these two should be counted as the same. And this time, each group contains 6 elements. They correspond to the 3 factorial ways to arrange the sun. So when these are gone, then you should divide it by 3 factorial as well. So if you understand this, so similarly, when there are 4 stars at the beginning, they are distinct, then this is the answer. But if the stars suddenly become the same, then we should divide it by 4 factorial. Is that okay? So this is another way to see why this is true. And for this one, we are using what? The quotient thing, the group thing. Okay, we group things together. We need to make sure that each group has the same number of items, and then we want to ask how many groups are there. Is that okay? Good. Now, if you are okay with this, so this is a warm-up to why this is true, and let me ask you a question. Okay, so this question is a little bit tricky. Don't try to get a single formula